Next up, we have Yujie from Department of Astronomy. Yujie is a second-year graduate student working on South Pole telescope data and millimeter transients in the galaxy. You ready?
Yes.
Let's give Yujie a welcome.
Hi everyone, I'm Yujie Wan. I'm an astronomy graduate here at UIUC and a current CAPS fellow. And today I want to present on the first galactic plane millimeter wave transient survey with SPT-3G. So here is the outline for my talk. I will start with the background for this survey, including why South Pole Telescope is great for this mission, previous results for transient surveys with SPT, and the motivation for a galactic one. I will then talk about the details and observing strategy for the galactic plane surveys. I will then move on to the preliminary results. I will briefly mention the data reduction steps we take, how we go from raw data to maps and then to transient candidates. Last but not least, I'm going to talk about future plans, including how we're going to proceed with data analysis, the plan to build a faster transient detection pipeline, and the plan to use this survey as a pathfinder for future experiments such as CMBS-4. So let's get started. The millimeter wave transient sky contains a lot of information on many astrophysical objects and phenomena, including stellar flares, varying AGN, long-duration gamma ray bursts, and more. However, the transient skies has traditionally been observed with optical, X-ray, and other wavelengths, while the millimeter wavelength remains largely unexplored and is constrained mostly to falloffs of transient events firstly detected in other wavelengths. Fortunately, the South Pole Telescope, which is shown here, has high enough cadence and sensitivity to be able to perform blind millimeter transient surveys to open up windows for new discoveries. Lots of people here are involved in SPT collaborations, but let me just say a few words about the instrument. It is a 10-meter diameter wide field telescope located at Munson Scott South Pole Station in Antarctica. It is primarily a CMB survey telescope. The observing strategy of regularly repeated observations of the same patch of sky make it also powerful for time domain science. It observes at 3 different bands centered at 95, 150, and 220 gigahertz, and it has angular resolution of about 1 arc-minute. Here I'm showing some previous results from transient sources with SPT. The first systematic search for transient events with SPT-3G has been conducted using 1 year of data covering 1,500 square degrees. The survey has found 15 transient events, including 13 stellar flares from 8 flaring stars. Some stars flare multiple times, and 2 extragalactic variable sources, which are likely AGN. On the left shows the light curves for all the stellar flares, and on the right shows the image of the associated stars from WISE with SPT contours overlaid on top. Till now, SPT transient surveys have detected hundreds of transient events. Most of them are galactic flaring stars, with also a few extragalactic sources. As for stellar flares, there is a recent paper coming out this year presenting a catalog of flaring stars using 4 years of data with SPT-3G. The catalog contains 111 stellar flares from 66 flaring stars. On the left shows the color magnitude diagram for the populations of stars. And on the right is the distance versus magnitude plot for the same population. So the distance ranges from 10 to 1,000 parsecs, which means all the stars are very nearby. So that motivates the galactic plane transient survey. All the previous SPT transient survey look outside of the plane towards the extragalactic sky. However, only a few extragalactic sources have been found, and most of the detections are local flaring stars. So if we look within the plane of the galaxy, we can see the Milky Way, where there are tons of stars and lots of other interesting stuff. People have been making observations towards the galaxy. Here are some examples. HIGAL, the Herschel Infrared Galactic Plane Survey, observes at 5 different bands, making photometric maps and also compact source catalog. Meerkat observes at 1.3 gigahertz towards the galactic center, and there are more. However, these were all static continuum surveys, and they were not in time domain. So the SPT-3G Galactic Transient Survey is the first time SPT looks towards the galaxy, and it is also the first millimeter wave galactic transient survey. We're expecting to see stellar flares based on previous results. And since we're now looking into the plane and not out of the plane, we're also expecting to see things we could not see before. So the survey covers a number of known X-ray binaries, so we might be able to see that. We might also see classical novae, magnetars, and maybe even things we don't know yet, which is very exciting. In parallel to this, there's also a separate survey measuring the variability of Sagittarius star. So let's talk about the observing strategy for the galactic plane transient survey. So the whole galactic field has been divided into 3 subfields, and the plot shows the position of the galactic fields on the sky. So the plot on the left overlays the fields on the whole sky and compares the galactic field, which is indicated by the blue boxes, to the main field, which is indicated by the purple region. And the red dashed line shows the galactic plane. So the galactic fields are all centered on the galactic plane, while the main field is clearly avoiding the galaxy. And the left image zooms in on the galactic fields and is in galactic coordinates. The same thing here, blue box shows the galactic fields, the green dots shows the Sagittarius star, and the orange region shows the galactic fields from ASCAP for comparison. So the survey field is limited by atmospheric loading, which determines how low we can go in elevation, and the location of the field are designed to go as low as we can in elevation, and also to maximize the overlapping area with ASCAP survey. So when observing each subfield, the telescope started at the highest elevation and scanned back and forth along line of constant elevation at a constant speed. After finishing each scan, the telescope takes a step in elevation and repeats scanning back and forth till covering up the whole subfields. And on each observing day, we observe all 3 subfields, and we started the galactic survey in March in 2023 for about a month, and we continued the survey this year, also in March, for about 3 weeks, and we just finished up the 2024 observations, and the plan is to observe the galactic fields for roughly a month every year in the future. So the whole galactic field is about 16 degrees wide and 10 degrees tall, and the total area is about 125.6 square degrees. There are about 500 observations in total for each subfield, measuring the intensity and linear polarization at 3 different bands centered at 95, 150, and 220 gigahertz. If we combine all the observations, the co-added depths can reach 5.6, 6.8, and 23 microkelvin arc minute for the 3 bands, respectively. Here shows the galactic plane parts for the field. And some of the famous objects have been highlighted in the field. Sagittarius star, which is the black hole in the galactic center. SPT-2 is the giant molecular cloud, and there are 2 nebula, Lobster Nebula and Cat's Paw Nebula. Now let's move on to the data analysis part. The general idea for the workflow for transient detection is as follows. So we obtain the raw data, the time order data from the telescope. We run the map-making pipeline to make individual maps. We combine all the individual maps together to make the average map, or sometimes called template map or co-ed map. We subtract the average map from the individual maps to make the difference map, and we run the transient detection pipeline on the difference map to find transient events and get light curves for those transient events. I'll now talk about each step more thoroughly. So the first step is to construct individual maps for each observations. The map-making pipeline we used is similar to the one we used for our previous transient survey. The pipeline converts the raw time order data taken by the telescope to maps for scientific analysis by weighting and binning the raw data. During the map binning steps, a number of filtering steps has been applied to reduce the noise in the data, which is primarily from the atmospheric emission. After the map binning steps, we then apply several calibration steps, including pointing calibration and gain calibration. And for the calibration steps, we picked several point sources in each subfields, which are very stable in position and also in magnitude. And we use those stable point sources as reference sources to construct pointing templates and to calculate the average detector signal. And we use that to correct for each individual maps. And here is an example of an individual map made from a single observation. After having all the calibrated individual maps, we can then calculate a weighted average for all the maps together to make the average map. And the weight for each individual maps is calculated from the variance of the raw data, so noisy maps has low weights. And here is the average map for the same subfield. And the difference map is made by subtracting the average map from the individual map. This will remove the CMB background, stable point sources, and leaves only transient and variable sources in the difference map. We then apply a convolution filter to maximize the sensitivity to point sources. Here shows an example of a difference map for after transient filtering for the same observation. As you can see, most of the static sources have been removed. And this is the movie showing the difference map for the whole galactic field. And the movie is in time order. So the contour basically shows the location of the galactic plane. And for sources within the contours, we think that the detection in the difference map does not mean they're transient in nature because like the galaxy is very bright, and especially those sources are very bright, and a tiny percentage of residuals from differencing will still be like several sigma in the difference map, and we're working on getting better. But what's important is that if we look outside of the contour, we can actually see things popping up in the movie. And for those sources, we think that they are real transients, and that's what we are trying to find. So normally we will run the transient detection pipeline to find transient events. The pipeline works like this. It finds pixels in the map above several sigma, usually it's 2 sigma. It extracts light curves for those outlier pixels. The light curves are then fitted to models to calculate test statistics, which is then used to infer the significance. And light curves with test statistics above the threshold will then be considered as a detection in the pipeline. We are currently running the pipeline, and we're also thinking of improving it, but that's all work in progress. So here we took another approach of visual inspection. We went through all the difference map, and here are 2 sources which we think look real. So the top shows the light curves for the 2 sources. The 2 colors shows 2 different bands at 90 and 150. And on the bottom shows the movie of the thumbnail of the sources when an event happens. So you can see the transition of the sources from being quiescent and then getting brighter and then getting back to quiescent again. We still need more investigation into the nature of the sources, but for the shorter one, we think it probably is a flaring star. So for the sources I just showed are all short-term transient events. And since we just had the 2024 observation finished several weeks ago, we can now look at long-term transient events by comparing the 2 years of data between 2023 and 2024. So this is the yearly difference map. The same thing here, contour shows the galactic plane, and I have highlighted the sources that shows up in the difference map. it is very exciting that we find many sources that change their magnitudes over years, and we're working on understanding them. So for future plans, we will continue the analysis for the 2 years of data, including running the transient detection pipeline, characterizing the sources we found, and cross-matching with other data archive such as Gaia and WISE. We also want to build a new, faster transient detection pipeline. So the current pipeline works on individual observation to build the light curve, which has timescale of hours. We're going to modify it to work on individual scans, which is like 1 minute. So this will significantly improve the sensitivity to fast transient events, for example, stellar flares. So the plot shows the light curves for a flaring M-dwarf stars. The gray dots are from TAS, and the blue and orange dots are from SPT. So the main panel shows the light curve extracted from the current pipeline, and the top panels shows the expected light curves from the new pipeline. So you can see that the new pipeline will have much higher time resolution and much faster cadence. So the work that I've been doing will also be important for CMBS4. So CMBS4 is the next generation experiments at millimeter wavelengths. It has 4 main science goals as listed here, and mapping the time variable millimeter wave sky is one of the 4 main science goals. Here shows the survey field for CMBS4. Different from the main field of SPT-3G, which looks at the extragalactic sky, the survey field of CMBS4 now is much larger and includes the galactic plane. So the galactic survey with SPT-3G will work as a pathfinder for how to deal with the galactic fields for CMBS4. And my work will be helpful for planning the future survey. And all the analysis tool built for finding galactic transients for this survey will also be useful for future surveys. And here is the summary. Thanks for your attention.
Question for Yujie. Liam.
Thank you, Yujie, for the great talk. Could you go? I made a note so I didn't forget. Could you go to the slide where you show the example difference map? And I feel like I've asked you this before, maybe when we were just talking about your work. So forgive me if I've just forgotten and you've answered this before. When I look at this, I see, or I think I see sort of like a sinusoidal behavior vertically, like sort of a waving back and forth in what otherwise kind of just looks like noise. Are my eyes playing tricks on me, or is that a real thing?
I think it's probably noise or like leftover residuals from the atmosphere. So, well, I think it's just noise.
Okay, thank you.
Thank you. Can you go to the preliminary results slide?
Yes.
I was just curious, do you know already what the one on the left is, what the source is? Or what type anyway? The difference in the time duration is like huge between these, so this is interesting.
Yeah. So we did a quick search, and the guess is X-ray binaries, but we're not so sure about that.
Awesome.
So I know you're still working on the data, but what transient do you hope to find as you get more data?
So we're expecting stellar flares, and I hope to find new things.
Will the 220 gigahertz band be available for this sort of survey in like upcoming? Is it planned to be able to have this capacity?
Yes, I think I haven't included the 220 because it's like noisy, but yes, it will be included in the future.
So ASCAP is working at lower frequency, but because it's an interferometer, I would suppose it has higher resolution potentially. So how are you complementing the ASCAP survey in terms of the types of sources you're sensitive to?
We haven't done that yet. I think we just like put our fields in the ASCAP survey so we can do it later, but I'm not sure.
So when you're detecting these transients, particularly if you're trying to speed up how quickly you can detect them, is the idea that you would be able to like characterize the type of transient or the physics in it using millimeter wavelength, or that you would trigger follow-up from something else to try to figure out what it is?
I think there is a trigger system that's worked at POL, and I think right now it's like 24 hours later it will get a trigger. And for this one, I think currently it's still like offline analysis. So we get the data and we run like single scan like hers, which is like 1 minute. Does that answer your question?
Yeah, thanks.